it.
Okay,
Or did I ever give you,
final guess.
I may have passed these out.
I think I've narrowed it down to 10 people.
See, I hope you have one of these. If you don't, no, I can't find
Yeah,
it.
I think maybe Emily or maybe myself.
Emily's
Do you
around
have
here.
this?
Adrian or maybe.
Yes.
Yes.
Will you get that out real quick? I don't think we've done this yet.
No, we did not. Yeah, you do.
No, we don't.
Yeah, you do.
Were you not supposed
Literally,
to pass
no,
that?
you don't. Emma doesn't have it.
Okay, I'm gonna have to share with one of you.
It's okay. Emma and I can leave.
Yeah, I can try to
I
get
dropped your pencil. I go, did you pick it up?
Okay,
Another.
all right, so let me take you back once again to the late 1600s when they had that aha moment that if you had velocity, that it actually had something to do with total distance or area. Or let's say if you had a rate of change, you could add it up over a certain period of time, and something like feet per second times seconds, because that's where your dx comes in. It's usually going to be a dt. Feet per second takes you back to some sort of total, okay? And then they realized, wait, we don't have to keep adding all this together. If we're able to, we can just take the antiderivative and figure it out, which you've heard from me many times. We know that today, so it's hard for it to be as earth-shattering as it took hundreds, thousands of years for them to come to this conclusion. It's really remarkable, and I'll show you different ways that they knew the area of like a semicircle, because they didn't have the formula 1/2 pi r squared or a sphere. And so they were really actually adding up a lot of polygons, a lot of rectangles or different things like that to try to get it. And then later on I'll show you they integrated to get the formulas. So once they figured out that they went hand in hand, it's really interesting to see. Remember, it's just displacement though, it keeps a running total. If you just go from A to B, you know, we talked about if you ran up here and then ran back here, and this was 10 miles and this was 6 miles, I would think you only went 4 miles if all I know is the beginning and the end. Do y'all see what I mean? I wouldn't know that you went 16 miles, which would be pretty phenomenal, right? Okay, so be sure that you know how to handle this correctly and what you're doing when you use it. Now, once that came about with Newton and Leibniz, there were these fundamental theorems of calculus that came into play. By the way, when I started teaching calculus, and I actually read in the textbook I was teaching out of that first year, a long, long time ago, I was 22 years old. Anyway, I can't remember, like, I started teaching when I was 21, I turned 22 during the year. I was teaching algebra 2 and something, I don't remember what else at school, and the headmaster came in and sat down and pulled up a chair. I was in my room by myself, you know, just grading papers or something, and Mr. Kane was like, Miss Bush is retiring at the end of the year, and we want you to teach calculus. And they're just like, calculus, which now I can't imagine not doing it, because it's really all I want to do, to be honest. But anyway, so I've been doing it for a long time. But I remember reading that book that next year, that I was pouring over my book every night, trying to keep ahead of the students. Fundamental theorem of calculus, and even the year before, I remember reading the fundamental theorem of algebra, and I went, why don't I know this? Like, I'm a math major, why don't I know the fundamental theorem of algebra? But some of you may be sitting there going, whoa, I'm really super smart at math. Anybody know the fundamental theorem of algebra? No. Isn't that shocking? Makes me feel better.
But I did learn it.
We all say it. We all say it in class. It's that if you have an x to the third, blah, 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 polynomial, there are 3 roots that make that true, that solve it. Some of them might be imaginary. Imaginaries come in pairs, you know, it went with all that stuff that you were learning. That's the fundamental, sounds pretty fundamental theorem of algebra. Fundamental theorem of calculus was like, whoa, wait a minute. We could just, the sigma, remember the S really meant sum. Instead of what you were doing before, adding up lengths times widths over and over again, which Leibniz, went like this. And the width is really just your change in x, wasn't it, these increments that you were doing? So the first fundamental theorem, shocking thing that people came up with, Newton and Leibniz came up with, is, wow, instead of doing all that adding up, will the antiderivative really just work? Can I really just go backwards from rate to original? Tried it a few times the quick short way and it works every time, okay? For your homework, you ran into some that you couldn't integrate. And I got a couple of emails like, I can't do these, and then they realized that it was a calculator active problem. That's what you'll run into on the second part of the multiple choice exam and on the second part of the free response and on my test, is they intentionally give you ones that you couldn't undo by hand anyway. Even if you could, I wouldn't want you to on the calculator active pages. I'd want you to type it in its purest form and let the calculator do the work, okay? No matter what your great operating system is on your calculator, all of us will find at some point that it really slows down when we're asking it to take an integral. Because, of course, they can't program every antiderivative into the calculator. Plus, we don't know a lot of them, okay? And so it wouldn't be able to answer the question for you. I think I've told you on Emily's fancy calculator, when she was using the 89, I could type in integral of tan x and hit enter, and it'll tell me what it is, which, by the way, is ln secant x, but we'll go over that later. It would just tell Emily and I what it was without the plus c. If Emily and I type in some other integrals, though, like cosine of x cubed, it'll just return it right back to me, the integral of cosine x cubed. I don't know the antiderivative of that. But if I take the integral of the cosine of x cubed from 0 to 2, we all should be able to do that somehow, right? Because at that point, we have a definite space that we're traveling, not an indefinite integral. So it's programmed, from what I can tell, to kind of go back to square one. And it's adding up a bunch of probably Riemann sums for every single thing that you type in. So the first fundamental theorem of calculus is that instead of doing this from A to B, and girls doing all that link comes with, link comes with, link comes with. Let's pause for a minute. You went home and successfully did a great job as a class doing like four or five of them. You were like, got this, I can add up these rectangles. You learned really quickly that mid was a great approximation and that trap was a great approximation, far better than left or right. But then you saw me twice actually find the real answer, because how many rectangles did I add up at the very, very end of those two treacherous problems? Do you remember I added up an infinite amount of rectangles? All of a sudden, instead of 6 or 60, I took the limit as the number of rectangles approached infinity, and I colored it in because the rectangles are paper thin, okay? So anyway, instead of doing what this means, the shocking part was, oh my gosh, could I really just go backwards and go to f of b, the original, minus f of a, and treat this like a derivative, okay? That's the first fundamental theorem of calculus, that you can go to the antiderivative. And if there's not an antiderivative, you can still find it, okay? Using the limit process. Now, having said that, I just want to, before we go over the second fundamental theorem of calculus, I want to talk about in what ways you're going to use this. I have no idea why it makes me do this twice, but it does. Okay, so if I see this statement, that's like a huge announcement with a megaphone that F is what? Sophia, F must be the derivative of G, right? If I walk up and say, I integrated G of X, I integrated F of X and not G of X, that must mean that this is G prime of X. And you know how I try to train you, for lack of a better word, to like get away from a graph and go to a plus minus chart of the object that you're talking about so your mind won't play tricks on you. I encourage you to do that right from the get-go if you see a statement like that. and write yourself a note. Everywhere there's an f of x, you're looking at the derivative of g. So behind here is some form of rate, okay? Like miles per hour, people per minute, when they do the crazy things like how many people came to an amusement park through gate B. We'll probably look at one of those later. But if I do miles per hour for 1, 2, 3, 4, 5 hours, do you see it takes me back to displacement at least, okay, total. And so look at this as a rate. So that's the first fundamental theorem of calculus. Now, of course, what came from that is another, what they came to call, it was a thing that people started doing, and then it came to be called the second fundamental theorem of calculus. Because if I teach you to square, and then a month later I teach you to square root, you've just learned what? Inverse functions. They come at a great price. The first inverse functions that you learned cost you nothing at all. Addition and subtraction. Nobody said give you any fine print with that. Like, oh, you better not, blah, 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 okay? But then what happened as soon as you got multiplication, what'd you get next? Division undoes it, but you got a tiny bit of fine print. You can multiply by 0, but you can't divide by it. Then you learn to square and do other exponents, even exponents, x to the second, x to the fourth, x to the sixth. And you got a lot of fine print for that one, because all of a sudden you can't square root half the numbers, right? Okay? Think about sine and arc sine, which a lot of people just still grapple with, I think, what in the world's going on with those. But when I go to push inverse sine, inverse cosine, and inverse tangent, it's only going to land me in 2 quadrants, whereas sine and cosine have a domain of all real numbers. So, I mean, it's severely limited, right? So, I think the second fundamental calculus will make sense to you, but I want to tell you there's some fine print, okay? It goes back to this. I've taught some students that insist that's -3. They're like, my teacher before you taught me that a square root would get rid of a square. So much so that the poor children have seen this. They've seen their teacher do that 1,000,000 times. And that's wrong. The square root of x squared doesn't equal x. What does the square root of x squared equal? Thank you so much. Absolute value of x. There's a math problem to be worked out here. I don't really care that it's a square and a square root. I care a little bit. I know that I maybe don't have to do so much work. Like, for instance, if I see this, I am glad I have inverse functions, okay? But I really don't have to worry with finding 117.3 squared just to square root it. The answer to this problem is 3. Do y'all undoubtedly believe that? There's a math problem we need to work out. If you type this into your calculator doesn't turn pink and go, well, it might be pink, but anyway, it doesn't turn all these rainbow colors and start flashing, thank you for giving me an inverse function. It doesn't know. It's going to do the order of operation, right? What's it going to do first? -3 squared is 9, and then when you square root 9, it returns you to 3. So the answer to this one is that, right? I can really not say that whatever I square, if I square root it, I return to what I put in. I cannot say that. Nobody should have ever said that. But it sure does confuse you, okay? If I go inverse sine of the sine of 240, my calculator will return to me -60. There's a math problem to work out here. I don't go, yippee, I have inverse functions. I do a little bit. I'm kind of glad I have them. But ever since division, you've had to be careful, okay? If you work this inside out, the sine of -240 is -√3 over, sine of 240 is -√3 over 2. And then your calculator and your brain should proceed to find the inverse sine of -√3 over 2. So all it knows at that point is that you're looking for an angle with a sine of -√3 over 2. You can see why all of this stuff had to come into play. Because you never get to use your calculator again if it was really capable of answering that question. Because how many answers are there to this question? if it's worded this way on the original function. There's an infinite number of answers. The calculator would be just spitting them out like this, okay? They're going on forever. But we kind of have a workaround. If we write it like that, it just at least gets us a star. Does anybody remember what quadrants we should look in?
1 and 4.
Very good. 1, we're not going to find it there, are we? So we go to 4 and find it at negative 60. So my point is, don't just do that with inverse functions, okay? Even this is not always true, right? I can cancel out those x's all day long as I state or make sure that the x is what? Not 0, okay? Which for the record, if x was 0, that would, if you multiply them, you would get 0 over 0, which is one of our 7 indeterminate forms, which means we just went into Narnia, whatever is in Harry Potter, I don't even know what it is. Okay, so I really always lay that foundation before I just bam show it to you, okay? But we gotta know that this is probably gonna cause something to happen. Do y'all see why this is so fundamental to what they discovered? They had no idea that integrals and derivatives had anything to do with each other. An integral is a summation tool, a derivative is a rate. But now they should sort of wipe each other out like a square and a square root, right? But don't forget there's a math problem to be worked out, okay? You're gonna see me do this a little bit today, right? It's a composite function when I have the square root of x squared. Y'all agree with that? So remember, when you have something like this, it's a composite function. You're supposed to take the derivative of whatever that integral was. When you integrate it, I'm gonna step over here. And let's say that I was going on a trip, okay? So I flew somewhere and I checked my luggage, all right? So when I arrive in that place, and that's a really bad example. Okay, so back over here. So I fly to, let me think of a fun place, Barcelona, where, oh my gosh, the shoes and the dresses there. Oh my gosh. Okay. Anyway, so I have my luggage, all right? Next time I go, it will be almost empty so that I can buy lots of stuff, okay? Like $7 shoes and junk like that. So anyway, go to Barcelona with my luggage. Here I am in Barcelona. What am I gonna do while I'm in Barcelona is buy dresses and shoes. Where am I gonna have to put them? In my suitcase. Sure enough, you see me and I come back to New York, but what am I lugging with me? All of my baggage, right? That I picked up over there. So I might even have an extra bag. Y'all see what I mean? It's still me, with my luggage. But when I was over here, I did something else, and I'm dragging it back with me here, okay? Stupid example. You're super used to that, so let's move on. All right, so the first one on your sheet. If you have the derivative of an integral from 1 to x of t squared dt. You're gonna hear me say this all semester. I've started saying it now. Follow your variable. When is class over? 1:20. Okay. Follow your variable, follow your variable, follow your variable. The answer to this is going to be x squared. Okay? These do cancel each other out, but while you were in Barcelona, it became a function of x. Okay, so I'm going to actually work the problem out. All right, let's work the problem. Let's take the antiderivative of t squared, which is t to the third over 3 plus c. But I don't need the plus c because I have limits of integration 1 to x. Do y'all see my composite function here? Okay, so now I've got to take the derivative of, now I put in top minus bottom. When I put in the top, I get x cubed over 3. And when I put in the bottom, I get 1/3. Now, what's the derivative of that? If I differentiate that, I get 3x squared over 3. And what's the derivative of a constant? 0. So we'll feel kind of silly if we don't kind of get what's going on, because why in the world did I go over there just to come back over here? All right? But did y'all see what I picked up while I was on my trip? While I was over there, I picked up x and 1. So do you see why it became a function of x? Did y'all see that? There's more to it than that, so let's keep going. Alright, so on the next one, anybody volunteer to give me the answer to the second one on the page? Let me get it written down first. Anybody? If I integrate cosine, it takes me to sine. If I differentiate sine, it takes me back to who? Cosine, but what did it pick up while I was there? Follow your variable. And it even says it right here. You're taking the derivative not with respect to t, but with respect to x. The answer is going to be cosine x. So it's, aren't y'all seeing right now, like, Mrs. Larry, why are you making such a big deal about it? It looks like to me they're canceling each other out, right? Okay. Now, if y'all believe that would happen if I worked it out based on the last one, antiderivative of, here we are, right here in New York, antiderivative of cosine, anti is sine, positive sine, but then I turn around and differentiate. However, when I was here, I picked up x and pi over 6, so it became a function of x on the way back. Watch out, girls. On your multiple choice answers, they're going to have all kind of things for people that don't really understand it as well as we do. Do you see I might make you choose between cosine x and cosine t? You should be sitting at your desk thinking right now, well, okay, fine, I'll just work them out every time and I won't worry about it. But that's not always going to happen either, so let's keep moving. Okay. So let's grapple with it a little bit more. Okay, so the second fundamental theorem of calculus, come on, I forgot one. If you have the derivative in the little box there, if it is just going from a to x of f of t dt, it will just take you back to f of x. I would integrate it, step over here and get some function, let's call it g. Then I would differentiate it and go back to f. So I am in some way trying to get you not to go over here, just to come back over here, okay? All right, now let's look at the next one. And I have a surefire way to where you won't miss these, so just watch, because I know all the tricky stuff they'll throw at you. That one is not going to be x squared. Anybody know what it's going to be? Negative x squared. All right, let's work it out. Let's work this part out. That would be t cubed over 3 from x to 4. And then after I finish that, I'm going to differentiate it. So while I work this part, it's going to give me 64 over 3 minus x to the third over 3. And now I'm going to differentiate that. Derivative of constant 0. The derivative of that's going to be negative 3x squared over 3, or negative x squared. A lot of you, I think 3 or 4 of you caught it was going to be negative without having to work the problem out. I got to get you to where you don't have to work the problem out, because they're going to be all kind of crazy stuff that either you can't integrate or you don't even know what the function is. So now let's do the next one. Okay. So the next one is d over dx. In the blank of the second box, the answer to that one would be negative f of x. If the x is on the bottom limit of integration, it would have been subtracted as you went. Are y'all okay with that in the second box? Okay, they cancel each other out, but there's a little bit of a price to pay. All right, now look at this one, at the third one. All right, any guesses what this one's going to be? Some would say, I'm not going to be upset if you guess the wrong thing. Most people would right now. But at least guess what trig word is it going to end up at? With something built into it? Okay. one of your answer choices will be cosine of x squared. Another answer choice they'll throw at you is just cosine of t and cosine of t squared. There'll be enough legitimate looking ones for you to go, oh my gosh, okay? And lots of people miss these. You will not be that person, okay? I'm going to predict the answer is going to be 2x cosine x squared, okay? We have a triple composite function going on here. If we work this one out, okay? So let's work this part out, and then we'll take the derivative of it. The antiderivative of cosine is sine of t from pi over 6 to x squared. That's going to give me the sine of x squared minus the sine of pi over 6, which is 1/2. Now let's differentiate this. What's the derivative of sine of x squared? You would hopefully not in your wildest dreams think that it's just cosine of x squared. It's cosine of x squared times 2x. Why have I not had to think about that before? That would be negative sine x, but the derivative of the inside, what's the derivative of x? Is just 1, right? Okay? So you have to see, and what's the derivative of a constant would be 0. All right, so look at this one. So anyway, I was right, and you'll be that fast at it in just a minute. Okay, so if I have the integral of u cubed du, let's make it 4u cubed du, from 2x to x squared, and I want to take the derivative in terms of x. Notice all my variables. I'm going to predict what it's going to be, and then we're going to check me. Okay? I'm going to predict, why would I bother going over there and just come back over here? I'm coming back to 4u cubed. Okay? While I was on vacation, I did stuff some things into my suitcase. Okay? I stuffed in x squared and 2x. And so on the way back, I better account for those. And I'll tell you how I predicted this in just a minute, but first of all, we're going to see if I'm right. I predict we're going to get 8x cubed minus 16x. So let's just hold that for a minute. All right, now let's actually work the problem. All right, so this is 4u to the 4th over 4 from 2x to x squared, and I'm going to take the derivative. Always keep an eye on your variables. This is going to be u to the 4th minus u to the 4th, and I'll take the derivative of it later. I'm going to put in x squared and 2x. So I'm going to take the derivative of x to the 8th minus 16. I missed something. X. I feel like I've missed something. Did I miss something?
Yeah, you have to divide it by 4. Well, because it wouldn't be u to the...
It would be 4u to the 4th over 4. Oh, I see what I missed. 4, I should have come back, I'm sorry girls, to 4u cubed. I just went back to 4u. I didn't go back to 4 blah cubed, 4 blah cubed. Okay, so that messed up my answer. So my prediction was wrong. So it should have been this. 8x to the 7th minus, that would be 8 times 6. Yeah, 8 times 8, 64. X to the 3rd. All right, sorry about that. So let me go down here and see if I get that. That's x to the 8th. That's 16x to the 4th. Now I'm going to take the derivative and get 8x to the 7th minus 64x to the 3rd. Okay? All right, so this is how I did it. I thought, I'm not going to go up here, just to go back to 4u cubed. Oh, that was kind of cool. cool. I don't even know how to. That was really nifty. Okay. I don't even know what's happening.
If you're not clicked on marker.
Thanks. Let me go. Okay. So this is what I did to predict. All right, I know that these are gonna cancel each other out to some degree. So I'm gonna go 4 blah cubed minus 4 blah cubed. But I have to keep into account, while I was over here at the antiderivative I'm not even writing down, I picked up some things in my suitcase, and now it's heavier when I drag it back, okay? And so I picked up an x squared and a 2x. So when I'm dragging them back, you see how I have to incorporate the chain rule into it, which would give me 2x times 2. So what I do is I just stay where I am. I fill in the things that I picked up, knowing full well that on the way back I would also encounter the chain rule. Okay? So let's write it down and then we'll do some more. Alright, so the second fundamental theorem of calculus at the very bottom. And I'm going to change it up a little bit. I'll go in and write in the box what they have right now, but I'm going to want you to write one underneath it that's more important. Alright, this eventually will become a function of x. But notice I'm going to be filling in a function into a function. Do y'all see a u of x up there? It might be like an x cubed or something, not just an x. I will come back to f of t, but while I was over here, I picked up 2 things. So I'm bringing them both back with me. Do y'all see what I mean? I picked up a top and a bottom. So I do come back to where I started from. But the top is filled in, and on the way back I have to compensate for its derivative. The bottom is a constant, and its derivative would be 0. So the answer would not just be f u of x, which I understand is really, really unfortunate notation right now, but let's move on. So anyway, I didn't realize that was going to happen. Moving on, we change those letters next year.
I literally wouldn't know.
Yeah, me either.
Yeah. I've taught high school for so long, I notice things so quickly. Because I used to hear like giggling or people whispering, and now I see it before you see it. So forget it. So anyway, all right, so this is what I want you to write underneath it with a little bit better notation, okay? You know, if I use A's, B's, and C's, I'm talking about numbers. If I use things like F's and G's and U's and W's, I'm talking about functions. Y'all okay with that? So if I have the integral underneath it, write this, of f of t dt, and let's say you're going from u to w, not 7 to 4, okay? And you're going to take a derivative of this. So this is w, like it might be x cubed, and this might be 7x. These are functions, okay, in terms of x. So these will wipe each other out. You will come back to f. Fill in the top, times the derivative of the top, compensating for the chain rule on your way back home. Fill in the bottom, times the derivative of the bottom. That'll work every single time. And I've written it somehow like that on your study sheet. I mean, which I don't even know if you're looking at yet, your study guide's got a wealth of information. All right, so now, oh, am I through?
Yeah.
Darn. Okay, well, I wanted to do A through D. Well, I know, I just give you a little bit of, oh, I'm not supposed to give you homework. Are the lessons and carols?
Yay.
So you sort of have A through D. Maybe do them that morning before class, but I won't check it. No quiz or anything.
Yay!
So your job is to bring your fundamental theorems of calculus, and we'll finish that up, okay? You will have homework over Christmas on like probably 2003 or something.
I won't be here next class, so it'll be close.
I'll record it, yeah. Bye, girls.
Bye. Have a nice break.
Okay, you too. Merry Christmas.